We begin chapter 4 with a motivating example. Let's look at this polynomial, t to the fourth minus t squared minus 2 over q. And suppose that we wanted to study it, and in particular, we wanted to have an understanding of the roots. So what are the roots? And maybe a more general question that we might ask here in a second is, how big of a number system do we need to have access to the roots? So we have these sort of two questions here. We first need to find the roots. So you'll notice that f is not irreducible. And I guess we have a word for that. The irreducible factorization of f over q is, with the irreducible factorization, t to the fourth minus t squared minus 2 factors as t squared plus 1 and t squared minus 2. Both of these terms here are irreducible. And let me just take a moment to notice something here. F has no roots over q, or no zeros in q, yet it is reducible. Okay? So just a cautionary, this mistake happens over and over again every time I've taught this class. Just be aware that just because you don't have roots doesn't mean you're irreducible. Okay? Nevertheless, it is a product of these two irreducibles here, and they are in fact irreducible because when you're degree 3 or less, degree less than or equal to 3, let me actually write out degree because that looks like a 2. Being irreducible is equivalent to not having any roots. So in this situation, irreducible is equivalent to no roots. And of course, the square root of plus or minus the square root of 2 are not rational, and the imaginary number I and negative I are not rational. So that is in fact its irreducible factorization. And so starting with q, so what are the roots then? The roots are plus or minus I plus or minus square root 2. So beginning with q, the smallest number system we might, well, how exactly did I say it? We asked the question, how big of a number system do we need to have access to the roots? Well, maybe that's not the best question. Let me change that to small, where small is something that we'll define later in a better way. Of course, if we had how big, that would be just all of C. We could just say that for all of our polynomials, and then we go home. But how small of a number system we need? Well, we need to have at least q, probably, because it has to be a number system, and q is the smallest characteristic 0 field. Okay, so we need to have at least q, but we also need to have access to at least one of the roots. So we need access to I. But if we have access to I in our number system, we should be able to multiply. So this tells us then we get access to the rational number -1 times I, which is negative I, which is the other root. So we throw in I, we get the other root for free. However, if we just look at the Gaussian rationals, so this gives us the Gaussian rationals that we've seen before. We showed this was a field in particular in chapter 1. The Gaussian rationals don't have a square root of 2 still, so you can check that the equation p plus qi squared equals 2 has no solutions in Q. Okay, you can write down some polynomial equations that must be true. By Gauss's lemma, you can assume that they're integral and whatnot. So, anyways, you can check that this doesn't work. Maybe not with exactly how I said, but it's possible to check this doesn't work. In fact, instead of me just saying it's possible, let's just do it real quick. So if you square that guy on the left, you get p squared minus q squared plus 2pqi equals 2. Or I'm going to choose to write that as 2 plus 0i. Okay? So we get p squared minus q squared is 2, and 2pq is 0. All right, so this last guy tells you p is 0 or q is 0. And if p is 0, then in this case, the first equation would say q squared is negative 2. Dang, I messed that up. Q squared is negative 2, which is impossible. And then in the second situation, if q is 0, this would say p squared is 2, which is impossible because p and q are rationals. There's no square root of 2 there. Okay, so this still has no solutions. So when we throw in plus or minus, when we throw in I, we get negative I, but we don't get root 2 and negative root 2. So we're going to go ahead and add in the square root of 2. And just like when we added in I, this gives us also negative root 2. Gives us all rational multiples of root 2 as well, if we're going to make a number system out of it. So by throwing in I and root 2, we get access to all of the roots. And I believe we did an example similar to this, but if not, you'll do these examples. So then when we do this process, we need sort of when we do this, what we get is a field that looks like the following. We have the rational still, but then we have to throw in I. But we also, when we do that, we throw in negative I. We also have to throw in the square root of 2, any rational multiple of the square root of 2. But also we have an I and a root 2. So we have to throw in I times root 2, which if you want to think about that as a single quantity, this is like root negative 2. So you have to throw in sort of 3 things, not just the 2, okay? Not just I and root 2. And this is P, Q, R, and S, R and Q. You have to throw in 3 numbers, not just the 2. Now this, it can be checked that F is a field. So F is a field. We won't check it right now. We'll have ways of checking it later. It's kind of the fact that this is a subring of C is fine. The closure under multiplication is a little bit tedious because you have to multiply out 2 expressions that are that have 4 terms. So you have 16 products. You'll find that it works out. The harder part is inverses. Okay, so I'll have we'll learn some tricks for finding inverses a little bit later on. All right, so what did we do? We started with this quartic polynomial. We wanted to understand how we might have access to the roots. That's what these 2 questions are saying. What sort of number system do we need to have access to the roots? We first had to find the roots, so we factored it as far as we could, and then we were able to locate the roots. And then we went sort of root by root, adding them in and seeing what that gave us. Okay? And what we arrived at is this field F. Let me notice one last thing before this introductory example is over. So also notice that Q is naturally a subset of F, where you look at the terms that are P and no I's and no root 2's and no I root 2's. In fact, it's a subfield of F. So F is a larger field that contains Q. So what we've done is we started with a number system and we threw in a bunch of roots and we got a larger field. Right? So what we're going to do in this chapter is this is really the type of example we're going to care about later, but we're going to study how you can enlarge fields in this way. These are called field extensions.